7175 is not one of the papers you just picked up. That's one of the papers that I gave you earlier. And I want to look at number 26. Okay? Number 26 starts talking about Coulomb's law again. All right? Evidently, they really want you to know Coulomb's law. All right? So just memorize Coulomb's law, and you'll probably get a 5 on the AP chemistry exam, I think. No, it's not that easy, unfortunately. But here it is again, right? Yeah, you need to know how to apply it. But it does apply to a lot of things. So it applies to ionization energy, okay? So if you look at this letter B here, the first ionization energy is the minimum energy needed to remove the least tightly held electron from an atom or ion, okay? I.e., valence electron, okay? In general, the ionization energy is the minimum energy needed to remove that electron, okay? In general. That's all we're going to worry about this year is in general. C, the relative magnitude of the ionization energy. You can use Coulomb's law to kind of think about this. The further the electron is from the nucleus, the more of a radius you have, which decreases that force, right? So you're changing the R here in this equation. To make it bigger, if you make that bigger, the potential energy gets smaller. The force gets smaller, okay? When comparing two species with the same arrangement of electrons, the higher the nuclear charge, in other words, you change Q1 or Q2 here to make it bigger, that's going to make the force bigger, right? So they just want you, yeah, force stronger, sorry. So that's what they want you talking about or thinking about with Coulomb's law and relationship to ionization energy, okay? So then you can do this stuff on the back, probably. It's just asking you to use Coulomb's law to explain why an electron further from the nucleus has a lower ionization energy and why higher nuclear charge. We just talked about that. So D, here's photoelectron spectroscopy again. I think we've actually already read this one. Yeah, so we probably don't need to talk about that again. Let's see. Do we have to talk about E? No, we already talked about E as well the other day. So, okay, 1B, 2B. I just remember liking, when I looked at this, I liked the way that they kind of explain, especially with D right here, the way that they explain ionization energy. I think their wording is good, and sometimes it's better than the book's wording on these particular issues. So for example, this one, core electrons are generally closer to the nucleus than valence electrons, and they are considered to shield the valence electrons from the full electrostatic attraction of the nucleus. This phenomenon can be used in conjunction with Coulomb's law to explain, rationalize, or predict ionization energies, okay? And then it says differences in electron-electron repulsion are responsible for the differences in energy between electrons in different orbitals in the same shell, all right? So the shell, when they say shell, they're talking about energy level, right? So like the rows on the periodic table, there's basically 7 shells that are possible in an atom, unless we end up making element 119 at some point. Then there would be 8 shells, right? So the reason I like this is because this is basically the effective nuclear charge thing that the book talks about, but I feel like this is a much, just a better way of talking about it, okay? So you've got the core electrons, and they basically block the valence electrons from some of the charge of that nucleus, okay? So if you think about that shielding effect that happens in conjunction with Coulomb's law, remembering Coulomb's law says the further they are from the nucleus, the less attracted they are to the nucleus. And also, the more of a charge the nucleus has, the stronger its pull on those electrons. Okay, so if you kind of remember those things, Coulomb's law and this shielding effect, it can really help to explain pretty much everything about the properties, the ionization energy, electron affinity, electronegativity, of these different atoms, okay, all those periodic trends that we talked about last year. So you just kind of have to keep, if you keep those two things in mind, you don't have to memorize any of the trends. You should be able to figure them out. That's kind of the point. All right. 1C1, C, and D. For many atomic properties, trends within the periodic table can be qualitatively understood using Coulomb's law. They're repeating themselves a lot here. The shell model and the concept of shielding. Okay. And so the properties that they say that you can really use this for are ionization energy, atomic and ionic radii, electronegativity, and typical ionic charges. All right. And then 1D, 1B. I don't remember what that is. Let me just look at that real quick. 1D, 1B. Construction of a shell model of the atom provides an opportunity to show how a model can be refined and changed as additional information is needed. So basically, the shell model of the atom had to be refined a little bit when we got this PES data, okay? Because what you start to realize, and we're gonna go over this a little bit more tomorrow, because I want to take some time with this PES data and see what it's actually telling us. But when we start to look at it, you can actually start to tell, hey, we can't just talk about first shell, second shell, third shell. There are actually some subshells here, okay, which correspond to the orbitals. So Bohr's model was not good enough, essentially is what this is saying. We have to refine it and use the quantum mechanical model, use Schrodinger's wave equation and those orbitals to really be able to describe what's going on in an atom, okay? And that model got refined to some extent because now we're able to collect this new data that wasn't fitting with Bohr's model, okay? So basically tomorrow, at the beginning of class, we're going to spend some time talking about how the PES data really does verify our model of the atom. And then we'll spend the rest of the time working on as many practice problems as we can. And like I said, I'll probably just record everything tomorrow so that those of you who aren't here, it'll be like you were here, right? Through the miracle of modern technology. All right, anyway, I'm going to go ahead and turn this off now. Goodbye. Goodbye.